In this video, I will give some hints towards solving an exercise where we use real experimental data from a molecule, sieve. A moist airflow of 0.065 kg dry air per second is dried in a column, 0.4 meters in diameter and 0.15 meters long, packed with 18 kilograms of zeolite with an exclusion limit of 4 ångström. The bulk density of the zeolite is 720 kg per cubic meter and its surface 1120 square meter per cubic meter. Holding the temperature and moisture of the incoming air constant yields the attached breakthrough curve and this temperature curve after correcting for the dead volume. The air moisture, kilogram of water per kilogram of dry air, is difficult to measure directly, but the breakthrough curve here has been calculated through measurements of the air temperature and the dew point. Regeneration of the column is done using hot air. A. Does the experimental data here imply that the adsorption is exothermic or endothermic? B. Continue your line of argument and explain why the breakthrough curve is asymmetric. C. How much water can be adsorbed in the column? D. If the breakpoint is chosen when the moisture is 0.05 kg of water per kilogram of dry air, what will the degree of utilization be? E. What will the degree of utilization be for a column twice as long, assuming constant pattern, etc.? So this molecule sieve is used to dry air, that is, remove water from the air. In this experiment, the temperature in the outlet varies with time. And the first subtask is to determine if this adsorption process is endothermic or exothermic, and that you should be able to do just looking at this temperature graph. But apart from telling you whether this process is endothermic or exothermic, this temperature graph also gives you a clue as to why the breakthrough curve looks a bit strange and far from the sigmoidal shape that we would like to see. Try to figure out how the temperature curve explains this strange behavior in the breakthrough curve. Now, let us look at this breakthrough curve. We are asked to determine how much water can be adsorbed. That is the same as determining the capacity of the column. So we do like we always do when we determine the capacity, we determine the area above the breakthrough curve. And instead of counting triangles and rectangles or something similar, we determine T star by drawing a vertical line and moving it around until the area above the breakthrough curve to the right of the vertical line has the same size as the area below the breakthrough curve to the left of the vertical line. Note that in our course it's good enough to make a visual comparison of the areas to find the T star. The area above the breakthrough curve will have the strange unit seconds times kilogram of water divided with kilogram of dry air. This unit you need to translate somehow into kilogram of water. The observant student might have realized that I stopped counting the area above the breakthrough curve at a certain point, despite the breakthrough curve continuing to wiggle about up and down. So why is that? Well, beyond a certain point, the noise in the measurement is of the same magnitude as the difference between the measured value and the maximum value, so we simply stop there. In task D, the breakpoint is chosen as the point when the water in the outlet is 0.05 kg of water per kilogram of dry air. Here, the area below the breakthrough curve is rather significant, so we need to calculate the amount of water that has come out. The probably simplest way to do that is to find a triangle with the same area as the area below the breakthrough curve. Note that there is a bump at the beginning of the graph. I have ignored that here under the assumption that that hump is probably an anomaly, and these are, after all, experimental data and measurements sometimes go slightly wrong. Furthermore, even if the initial measurements are correct, the area below that hump is negligible. In the last task, we are asked how the degree of utilization will change if we use a column that is twice as long, assuming constant pattern, etc. One way to do that is to calculate the length of unused bed in the first column, LUB, and consider what happens with LUB if we have constant pattern and the same linear velocity in both columns.